In this lecture, we're going to continue our program of looking for tools that we can use to sketch the graphs of polynomial functions. And this particular theorem that we're talking about here, the rational root theorem, the name kind of gives it away. This is another tool that we can put in our toolbox for finding the roots of polynomials. Now, our discussion of the rational root theorem is going to come in two parts. This lecture is very theoretical. We're actually going to prove the rational root theorem here. If you're looking for examples, or if after we stated the theorem, it's maybe not entirely clear what it's saying, then you might want to jump over to the other lecture in this pair where I go over some examples, right? So you can see how it's actually used in practice. That'll maybe give you a better idea of what we're talking about if just the statement doesn't make it clear. So here we have the actual rational root theorem. Now, a lot of textbooks, I mean, they have the theorem, but they kind of gloss over it pretty quickly, and they try to kind of jump right into doing specific examples or applications of it. But if we're going to prove this thing, then we need this very exact definition here. So let's see what this says. Suppose p of x is a polynomial with integer coefficients. Then every rational root p over q, and this is kind of our standard way of writing a rational number, right? So p and q first are going to be integers, and second, we're going to assume the fraction is reduced, right? That it's in lowest terms. In other words, p and q don't have any factors in common, nothing we could reduce or cancel out. And more specifically, and this is going to be important down the road, p itself does not go into q evenly, and q itself does not go into p evenly. So kind of put those facts in the back of your mind, right? Because they're going to be important a little later on. So if p over q is a rational root, then two conditions are met. First, the numerator, the p number, is a factor of the constant terms, the number at the end of the polynomial. In other words, it divides it, or it goes into it evenly. And q is a factor of the leading coefficient. That's the number out in front, right? So both of these two things have to be true. So that's how we can prove this, all right? First, I have here just kind of our generic polynomial. A sub n x to the n plus a n minus 1 x to the n minus 1, and so on, all the way out to a sub 1 times x plus a sub 0. So remember now, we're assuming that p over q is a root of this thing. In other words, if I substitute p over q into here for x, then the whole thing has to simplify to 0. All right, so let's do that. This becomes a sub n p over q to the n plus a n minus 1 p over q to the n minus 1, and so on. I'll do n minus 2. So that's a 2. Now, here's my next step. I'm going to do what we often do when we're working with fractions, or when we're working with anything that has fractions in it. I'm going to eliminate them, right? I'm going to multiply both sides of the equation by q to the n power. And that's going to eliminate all of these denominators. So let's do that here. And again, over here. Okay, now distribute, right? When I distribute to here, the q to the n's cancel, and all that's left is a n p to the n. And when I do it here, all right, there's only a q to the n minus 1 here. So I'm left with a n minus 1 p to the n minus 1 times q plus a n minus 2 p to the n minus 2 q squared plus, and then down here at the very end, a sub 1 p q to the n minus 1 plus a0 q to the n still equals 0. Okay. Now, here's the slick step. All right, I'm going to take this a0 q to the n that's down here on the very end, and I'm going to subtract it from both sides. I'm going to move it over to the left-hand side. So let me do that. I'm going to get this, right, and it's going to become equals minus a0 q to the n. Okay, now take a close look at that left-hand side, right? You'll notice every term on the left-hand side has a p in it. Okay, that means I can factor that p out, right? And then here's what I'm actually going to do. Let's divide both sides by p, right? So every term over here, every term, right, the whole thing gets divided by p. All right, so what happens? I get a n p to the n minus 1 plus a n minus 1 p to the n minus 2 q plus a n minus 2 p to the n minus 3 q squared, and so on, right? Down here to the very end, when we get a1, and both these p's cancel, there's no p anymore, q to the n minus 1 equals this thing. Oops, that should be a q, not a p. It's going to be p, q to the n over p. Now, that did it, right? Believe it or not, that did it. That was the key step. Look at the left-hand side. All of these a numbers are integers. All these p to a power values are integers. Q to a power is also integers. The left-hand side of this thing, it's big, right? It's got a lot going on, but the bottom line, this thing simplifies to an integer. Okay, well, if the left-hand side is an integer, then the right-hand side must also be an integer. Okay, now, here it is. Okay? P does not divide q to the n. You remember I said way back, I told you put this idea in the back of your head. P over q is a reduced fraction. P does not go into q, which means P does not divide q to the n. All right, well, the only way this thing is going to turn into an integer is if P divides a sub 0, and that is exactly what I needed to show in that first step. Okay, so now we're halfway done, right? That showed the first of these two criteria. All right, so now I'm going to clean everything up. Right? It got a little messy, so I'm going to go back. This is the line after we multiplied through and cleared out the denominators. All right, now from here, I'm going to do something very similar to get the second criterion. All right, I'm going to take this term and I'm going to move it to the other side of the equation. This will turn into a n minus 1 p n minus 1q plus a n minus 2 p to the n minus 2q squared plus so on a1 p q n minus 1 plus this constant term equals negative a n p to the n. Now, I'm going to use the exact same trick, right? The exact same technique. I'm going to divide both sides by q this time. And look at what happens on the left. Stuff starts to cancel. I get a n minus 1 p to the n minus 1 plus a n minus 2 p to the n minus 2 times q plus all the way out here a1 p q to the n. Plus a0 q n minus 1. Excuse me, this is not Q, this is Q n minus 2. There we go. I had a feeling that was off. Equals negative a n p to the n over q. Okay, but now look, it's the exact same argument. This left-hand side is a product and sum of integers, which means it must be an integer. And if the left-hand side is an integer, then the right-hand side is an integer. And since q does not divide p, the only way this fraction reduces to an integer is if q divides a sub n. And that is our second criteria that we were looking to show. And that's it, right? There you go. That completes the proof. Okay, so now where are we going next? If you haven't already, you should check out the second lecture in this series. It's the one where we do some examples and see how you can actually use this rational root theorem to find the rational roots of some specific polynomials. If you have checked that one out, then our next step is to add yet another tool to our toolbox. There's several that are going to be going on in this section on roots. The next one is called Descartes' rule of signs.